All right, so we are going to work on this problem from class today. So in part one of the question, the velocity stays the same throughout. I'll do one example here of calculating the momentum, and then we'll walk through each of the position calculations. So momentum, remember, is mass times velocity. The mass we're given in this problem is 1.5 kilograms. So if I do that multiplication, 1 times 1.5 is 1.5, 2 times 1.5 is 3, 0, and that's in kilogram meters per second. And then, since the velocity is the same for all of these, momentum will be the same also. To get the position, I'll use the position update formula. So, at t equals 0.1 seconds, x final is x initial plus v delta t. So an x initial is, for this time step, 0.500. V delta t, v is 120, and delta t is 0.1. And when I do that multiplication and addition, I end up with 0.7, 0.20. So let me write that up here so we have it. At t equals 0.2 seconds, my x final is the position at 0.2 seconds. X initial is the position at 0.1 seconds. So I'm using 0.1 as my initial for this next step. And so that initial was 0.7, 0.20. Velocity is still 120, and delta t is, again, 0.01, because it's a change of 0.1 seconds to get from 0.1 to 0.2. And when I do this, when I multiply out the velocity piece added to the position, I get 0.8. No, I don't. I get 0.7, 0.20. Let me go back and fix this. It was not 0.7 for the first century. It was 0.6. 0.6 up here. Again, another reminder of why, for the most part, we're not going to do these calculations by hand. We're going to have a computer do them. And so at t equals 0.3 seconds, again, I'm using the previous position, so the position at 0.2 seconds, as my initial. Let's see, so my initial at 0.2 seconds, or my position 0.2 seconds is the initial, plus v delta t. The position at 0.2 was this. V is still 120. Again, delta t is 0.1 seconds, because it's 0.1 seconds from 0.02 to 0.03. Do the multiplication, add things together, and you should get 0.8. Come back to the y in a second, and 0. So let's see here. I had the y correct at 0.1 seconds, at 0.2 seconds. This should be 0.4, and then 0.6. Okay, let's move on to part 2. So part 2 is not too different, except that the velocity is changing. So first thing that means is that the momentum is going to be different for each of these. Again, I'm doing mass times velocity to get the momentum. And so first one's the same as above. Unit here is kilogram meters per second. For the next velocity, again, I'm going to take the mass 1.5, multiply by this velocity, and I get this. Similar thing for the rest of these. I'm multiplying mass 1.5 times the velocity, and then these are the numbers that I get. Next up, let's see, we're going to need to do these positions. And for the positions, we'll use the position update formula again. And I'll try to be a little more careful this time about making sure I get exactly the right values. So at t equals 0.1 seconds, the couple things. One is we're going to do x final. We're going to use the position update formula. So x final is x initial plus v average delta t. In this case, now the velocity is changing. So for v average, I've got a choice to make. Do I use the velocity at 0 seconds, which is 120, the velocity at 0.1 seconds, which is 220? Do I use something else, like the average of those two or something? The answer turns out to be that you use the velocity at the time you're trying to find the position. So we'll use the 0.1 second velocity. So if I put in xi is 0.500, for v I'm using 220. And let me be a little more careful and put in units this time, meters and meters per second, times delta t is 0.1 seconds. And if I add those together, then what I get for the position is 0.7, 0.20 meters. So let's write that up here. So position is 0.7, 0.20. Positions in meters, velocities are in meters per second. At t equals 0.2 seconds, again, I'm going to use position update. So x final is x initial. What I'm going to use for initial is the previous position. So that's 0.7, 0.20 as the x initial. Velocity, I'm going to use the velocity at 0.2 seconds here. So that's 320 meters per second times delta t is again 0.1 seconds because it's the difference between this time and the previous time. When I multiply the velocity and time, add that to the previous position, what I get is 1.0, 0.40. The last step, going from 0.2 to 0.3, is similar. You'll use this position we just found as your x initial. You'll use 420 as the velocity, and when you do that, you end up with 1.4, 0.60 as the final position. So now let's take a look at part 3. So part 3, things are a little bit different. We're given, in this case, we're given a force. And at each new time step, the order that we're going to do things in is we are going to first find the momentum at that new time step using the momentum update. So let's start writing this down. So at t equals 0.1 seconds, we're going to first find the new momentum using the momentum update, calculate the new v from the definition of momentum, and then we're going to find the new position using this new velocity we just calculated. So let's start with finding the new momentum. The momentum update formula is PF is P initial plus F net delta T. So P final is the initial momentum we're given is 1.530 kilogram meters per second. F net is 500 newtons times delta T is 0.1 seconds. If I add those, so let's see, 0.1 times 5 is, 5 times 0.1 is 0.5. And so the final momentum here is 2, 3, 0. So this makes sense to me that the y component did not change because there is no force in the y component. Next up, we calculate the new velocity using the definition of momentum, v is p over m. The mass, remember, is 1.5 kilograms. And so if I divide this momentum we calculated by 1.5, then I get roughly 1.3320 meters per second. And now to find the new x, we're going to do the same thing we did in part 2 and in part 1. We're going to use the position update formula and this time, let's see, our initial position is 0.500. What we're going to use for v is the velocity at the time 0.1, which we just worked out to be 1.33, 2,0 meters per second, and the time step is 0.1 seconds. Multiply those two, add it all up, and I get 0.63, 0.20 meters. Left up the meters there. So let me write this up here. Okay, so to go to the next time step, we repeat this whole process over again. So one of the important things to take away from this is that it matters what order you do these in. You want to update the momentum, calculate the new velocity, then the new position. And so, let's see, so at 0.2 seconds, the new momentum is the previous momentum plus F net times the time difference. The previous momentum that we calculated was 230 kilogram meters per second. F net stays constant at 500 newtons. And delta T is 0.1, not 0.2, because it's the difference between this step and the previous step. Do the multiplication and addition, and you end up with 2.530 kilogram meters per second. Again, it makes sense to me the y component is not changing because the y component of the force is 0. So let me add this to our table of results. Get v the same way we got v before. Divide the momentum by the position, momentum by the mass. The mass is 1.5 kilograms. When I do that, I get 1.6720, and then I'll update the position, again using the position update formula. The initial position, I'll use the answer I got in the previous part, so 0.63, 0.20 meters. And the v I'm going to use is the v for the time I'm interested. So up here it's 0.2. And the velocity at 0.2 we just figured out was 1.67 approximately 20 meters per second times delta t is 0.1 because that's the difference in time between the two times. When I put those into my calculator, what I get out is 0.8, 0.40 meters. And last but not least, we'll find the momentum, velocity, and position at 0.3 seconds. So you're probably getting the hang of this now. The final momentum at 0.3 is the momentum at 0.2, which was 2.530. Add on F net, which is 500 newtons. Delta T again is 0.1 seconds. And I get 330 kilogram meters per second as the momentum. Divide that momentum by mass to get the velocity, and I get 220 for the velocity. And the very last thing is the position. X final is X in the previous step, so that was 0.8, 0.40 meters plus the velocity I put in is the velocity we just calculated, so 220 meters per second times the time step. It's been 0.1 seconds since the previous step. Do the usual multiply and add thing, and I get 1.0, 0.60 meters. So let me write that up there. So one of the takeaways from this is that if you break it down into small pieces, this position and momentum update is fairly straightforward. It's very easy to make small mistakes along the way, but this is the kind of calculation a computer is excellent at, which is why we incorporate some programming into the course so that we can study some physical systems where it's difficult to study them pencil and paper, but it's fairly straightforward to program this approach into a computer and make the computer do the hard work of calculating the numbers.